Okay, so hello and welcome back. So in this video we will continue the concept of binary operations on binary operations that we were doing before. So in the previous video we talked about associative, we talked about the definition of a binary operation being associative. And so let's now take an example. For example, example number 36, which is a binary operation star on set A. Example number 36, which is show that addition and multiplication are associative binary operations on R. Show that addition and multiplication are associative binary operations, on R. But subtraction is not associative on R. Division is not associative on R star. Division is not associative on R star. Okay. Now, in order to show that addition and multiplication are associative binary operations on R, the definition of a binary operation being associative, we said that this was definition number 12. This was definition number 12, where we said that a binary operation star on set A is said to be associative, if A star B star C is equal to A star B star C for every A, B, and C belonging to A. This was the definition that we had. And so using this definition, now if you want to show that addition and multiplication are associative on binary operations on set R, of course you know that, for example, if you pick any real numbers, when you say R, basically you are talking about the set of real numbers, of course. So when you're talking about the set R, suppose that, for example, you pick any three numbers in the set of real numbers, for example, 2, 3, and -5, right? These all belong to R. Now, you know that basically, you know that A star B star C as far as basically addition is concerned. So if I say that if I'm talking about addition as a binary operation on the set of real numbers, I would write it as addition on the set of real numbers, and so in this case, basically A comma B gives, of course, this is addition, right? So A comma B give basically is mapped to A plus B, right? So then in this case I can write A star B, addition being basically star here, right? Addition being star here. So I can say that A star B star C, I can write it as either A star B star C, or I can write it as A star B star C. Because first you have to do the operation on two operands, and then take the result over there, and then take the third operand, and so on and so forth. Now, taking A star B star C, would be equal to, I'm talking about basically addition, so that would be A plus B plus C, and A star B star C would be equal to A plus B plus C, right? Now, so the numbers that I chose here were, and of course you know that basically addition in the set of real numbers is of course commutative, meaning that you can generally write A plus B plus C is actually equal to A plus B plus C, as long as A, B, and C are belong to the set of real numbers. Any other set that you're working on, the same thing applies there as well. So which means that basically addition is a binary, which means that addition is associative binary operation on R, and therefore addition is an associative binary operation on R. And moreover, what you can do is that for multiplication, you can still do the same thing, meaning that if I define a binary operation on the set of R's, which is R, which is multiplication, and if I say that multiplication as a binary operation on the set R, this means that A comma B, any A comma B belonging to this set is mapped to A times B, right? So that means that basically then if I'm talking about now here we are basically talking about three operands. If I'm talking about three operands, A star, B star, C, again I can write it as, first I either have to take these two together and then basically continue with the third operand, or take these two together and then take the result here and continue with the first operand. Meaning that I can write it as A star, B star, B star, C, or I can write it as A star B. I can write it as A star B star C. Which means that now when star is basically multiplication, A star B star C, written this way, is equal to A times B times C. And when I write it this way, if A star B star C is equal to basically A times B times C. And of course you know that A times B times C is the same thing as A times B times C for every A, B, C belonging to the set of real numbers. Which means that basically multiplication I'm sorry, I made a mistake here. Which means that multiplication, okay, is an associative binary operation on R. Okay, so that is that. And now here we also need to show that but subtraction is not associative on R. Meaning that, suppose that for example you write, of course subtraction is not associative because, for example, when you write A minus B minus C is not necessarily the same thing as A minus B minus C. It could be probably the same thing. I don't really know if that can ever happen, that these two can be the same values. But generally, for example, if you have A is equal to 2, B is equal to 3, for example, and C is equal to -5, then A minus B minus C is equal to 2 minus, for example, 3 minus -5 is +5, which is equal to 2 minus 8, which is equal to -6. And A minus B minus C is the same thing as 2 minus 3 minus -5. which is equal to negative 1 plus 5, which is equal to 4. So you can see that negative 6 is not the same thing as 4. And therefore, you can say that subtraction is not an associative binary operation on R. Okay, then that's about subtraction. And division is not associative on R star. Now R star is basically the non-zero real numbers, and we are talking about division. So division so suppose that I write A star B star C, and we are talking about basically the set of R star, which is non-zero real numbers. Now, since we are talking about that set, 0 is not there, meaning that I can write this as A divided by B divided by C, or I can write it as A divided by B divided by C. Now the division, when you do the division this way, so first, for example, let's take A, B, and C as the same numbers here. So for example, let's take A as the same numbers that we had here. 2, 3, and negative 5. Let's take A as 2, let's take B as 3, and C as negative 5. And when we do so, then this is going to be equal to 2 divided by 3 divided by negative 5, which is equal to 2 divided by negative 3/5, and that's the same thing as 2 times negative 5/3, which is equal to negative 10/3. Right, so of course division itself is a binary operation on the set R star, because you can divide and basically the operation is going to be a function. There is no problem with that, meaning that the operation is going to be a function. But it's not going to be associative, because as you can see, for example, here A divided by B divided by C is negative 10/3 here, and this one over here is now equal to, for example, 2 divided by 3 divided by, for example, negative 5, which is equal to 2/3 divided by negative 5, which is equal to 2/3 times negative 1/5, which is equal to negative 2/15. Now, of course, negative 2/15 is not the same thing as, and you know that negative 10/3 is not the same thing as negative 2/15, and therefore division is not an associative binary operation on R star. So That is all about that. Now, example number 37. Okay, so example number 37. Example number 37 is show that you want to show that star as a binary operation on R. As a binary operation on R given by A star B. A star B is mapped to A plus 2B. A plus 2B, and when I say I map to, I don't really know what is the proper way of reading this, but you need to understand the definition here. Otherwise, of course, it has to be read in the proper way. But since I don't really know how to read this thing, I'm just choosing some way to read it, because otherwise it wouldn't be possible to go any forward. But let me give you the definition. Let me give you the definition here from the very beginning. We said that basically definition number 10. Definition number 10, we said that a binary operation star, on a set A is a function. On the set A is a function, and basically the function is a function star. Star basically you can call the function star from the set A, from the set basically the Cartesian product of A and A to the set A, meaning that the domain of the function becomes the Cartesian product of A and A, or basically whatever the set might be, to the set itself. So the codomain of the function becomes the set itself, right? And then basically we said that we denote star of A comma B. We denote star of A comma B as or by A star B. So what that means is that basically, suppose that you have some function, for example, suppose you have some function f from A to B. This is a normal function. Let's say that we are not talking about binary operations and so on and so forth, just a normal function from A to B, f from A to B. So this function from A to B is basically a type of relation from A to B, and a specific type of relation becomes a function, as you know. Meaning that if the relation is in such a way that every distinct member of A is the pre-image of a distinct image of a distinct image in B, then we call that relation a function, and we write it as f is a function from A to B. Now, since this thing over here is basically a general definition that we are talking about here, definition number 10, if you have some function from the Cartesian product of some set to the set itself. And basically, if this happens to be a function, suppose that you have, for example, some suppose that you have this star from the Cartesian product of A to A. Now, A is some set over here, right? Some set over here. So you take the Cartesian product of A and you put it over here. And then the A itself comes over here. And then depending on what this star is, then this becomes a function or does not become a function. If depending on the set that you have, and depending on the operation that you have here, this becomes a function, then you can say that basically star is a binary operation on A, right? And here you can write basically A star B. You can say that A star B is given by, so basically whatever A comma B you pick here, so this set, the Cartesian product of A and A is going to give you all of these ordered pairs A comma B. So whatever A comma B you pick here, this becomes the input of this star operation, and it will give you basically something depending on the rule of that binary operation. For example, in this case it is A plus 2B, meaning that any A and B that you pick here, A is added to 2 times B, and that becomes your basically the image of A comma B under this rule, right? So that is basically the whole story here. Now, so basically this is important to understand, that we say that the binary operation star on a set A is a function. So a binary operation star on a set A is a function such that basically star is a function from the Cartesian product of A to A. And then we denote the star of A comma B as A star B. If you understand this much about this whole situation, then you understand the notation, and then it doesn't really matter how I read, for example, this part, then you know what that means. So for example, what this means is that A star B is equal to A plus 2B. When I say that A star B is equal to A plus 2B, and that is the same thing as A star of A comma B. That means that any A comma B that you find in the Cartesian product of R and R is going to be equal to A plus 2B, right? So that is basically the whole story here. Now, now that we understand this part, so let's get back to example 37. We said that show that star given by as a binary operation on the set R given by A star B is basically A star B is well, you can say is mapped to, or whatever, however you want to read it, A plus 2B, and A plus 2B, and what is the rest of the question, is not associative. Is not associative, right? Is not associative. And the solution is that Well, of course, you need to show that. So, for example, you pick three elements from. You pick 3 elements from. So when we are talking about a binary operation being associative, of course you're talking about three different operands, of course, meaning that you have some A, some B, and some C, and meaning that I can write basically A star B star C, and if I want to calculate this, of course I'm dealing with ordered pairs of A and B here, right? So that means that I can take this as, I can write this as either A star B star C, or I can write it as A star B, or I can write it as A star B star C. And then in this case, this becomes, for example, this part over here becomes, for example, your B. Your B in normally you write A star B, right? So A star B, you have basically, and this comes from A comma B, and that is basically the star of A comma B is equal to A star B. So now I have to basically, here I can take basically B star C, I can take it as B over here, for example, in this expression over here. And I know that the way that I'm talking about this is a little bit messy, but once we do a couple of examples, you will get the hang of this, of course. So now what this means is that A star B star C is the same thing as A star B, right? So first I need to calculate this part, which happens to be in a pair of parentheses, and then again I need to calculate A star and whatever I get over here, right? And the same thing applies here, meaning that first I have to calculate A star B here, whatever that might be, and then take the star of whatever that is, and C. So what that means is that now A star B star C is the same thing as in this situation. So we said that A star B is basically A plus 2B, right? So which means that B star C is basically B plus 2C, of course, right? Now let's take 3 values for A, B, and C. For example, 8, 5, and 3. Let's say that A is equal to 8. Let's say that B is equal to 5, and let's say that C is equal to 3, for example. Then this becomes basically so first I have to calculate this part, which is A star. Now B star C is the same thing as B plus 2C. So let me write this as basically A, which is equal to 8 star. Now B star C is the same thing as B plus 2C. So that's 5 plus 2 times 3 which is equal to 8 star. 8 star basically 5 plus 6. So 5 plus 6 is equal to 11. So this is the same thing as 8 star 11, which is again equal to basically 8 plus 2 times 11, which is equal to 8 plus 22, which is equal to 30. Right? Which is equal to 30. Now, if I want to calculate 8 star, basically A star, B star, C, if I want to calculate A star, B star, C, I need to calculate this part first, and this part becomes based on what we have over here. This becomes A plus 2B, right? So A plus 2B is basically here is 8 plus 2 times 5. 8 plus 2 times 5 star C, which is equal to 3 here, right? So this is equal to 2 times 1 is equal to 10, 10 plus 8 is equal to 18. So that is 18 star 3. 18 star 3 based on what we have over here is 18 plus 2 times 3. Is 18 plus 2 times 3, which is equal to 6 plus 18 is equal to 24. And as you can see, A star, B star, C, which is what we got over here, is not equal to A star B star C. And therefore, the operation star, star is not associative. Is not associative, of course, on R. Right? So now, as a remark, we can say that the associative property of a binary operation is very important in the sense that with this property of a binary operation, we can write A1 star, A2 star, all the way up to A of n, which is not ambiguous. But in absence of this property, the expression is ambiguous unless brackets are used, right? Recall that in the earlier classes, brackets were used whenever subtraction or division operations or more than one operation occurred. Now, so as a remark, we can say that the associative property of a binary operation a binary operation is very important in the sense that with this property of a binary operation, with this property of a binary operation, binary operation, we can write A1 star A2 star all the way up to star A of n, which is not ambiguous. But in absence of this property, in the absence of this property, the expression A1 star A2 star all the way up to A of n is ambiguous unless brackets are used. I recall that, and of course you can recall that in earlier classes, brackets were used whenever subtraction or division operations or more than one operation occurred, meaning that you had we had brackets whenever we had subtraction or division, or basically whenever more than one operation occurred. More than one operation occurred. So what that means is that of course when you're doing subtraction or division, you have to use brackets, otherwise your statement is going to be ambiguous. Or when more than one operation occurs, then of course there is this rule that first, for example, you have to start from the left hand side, and then some operations take precedence over some other operations, and if you want to basically override that rule, those natural rules that we have in algebra, then you have to use brackets in order, and then whenever you have brackets, then brackets take precedence over the natural precedence of those operations, basically. So now let's 212, 213. So for the binary operation addition, on R, the interesting feature of the number 0 is that the number 0 is that 0, a plus 0 is equal to a is equal to 0 plus a. Is that a plus 0 is equal to a is equal to 0 plus a. So a plus 0 is the same thing as 0 plus a, which is equal to a, right? that is any number remains unaltered by adding 0. Any number remains unaltered by adding 0. But in the case of multiplication, the number 1 plays this role. The number, instead of 0, we have the number 1 plays this role. Meaning that 0 is the, I think we called it the identity of addition, and even the identity of subtraction, if I'm not mistaken. And 1, I think we called it the identity of multiplication, because 8 times any number times 1 is equal to that number itself, right? As this role. So, but in the case of multiplication, the number 1 plays this role, as 8 times 1 is equal to A, is equal to 8 times 1 is equal to A, is equal to 1 times A, for all A in R, for every A belonging to the set R. Now this leads to the following definition. This leads to the following definition. Definition number 13. Definition number 13. Given a binary operation star on A, star on A, an element E belonging to A, an element lowercase e belonging to A, if it exists, is called identity for the operation star. Is called the identity for the operation star if A star E is equal to A, is equal to E star A, for every A belonging to A. So then as a definition you can say that basically, given a binary operation star on A, that is, a star as a binary operation on A, an element E belonging to A, if it exists, is called the identity for the operation star, if A star E is equal to A is equal to E star A for every A belonging to A, right? So that was definition number 13. Now in the next video we will talk about some examples. We have a couple more definitions, just one more definition here, and some more basically material here that we will cover in the next video. I'll see you in the next video, and thank you.